السلام عليكم يا شباب.
عليكم السلام ورحمة الله دكتور.
طيب. بسم الله الرحمن الرحيم. So we're continuing. If you remember last time we were talking about the concentrated parabolic or the compound parabolic concentrators, the CPC, where basically it is made up of as if we have two parabola that are brought face to face. This is one of them, like this. And there's another parabola which is facing us like this. And at a certain time, we truncated it, or we just cut it down and we put our surface here. The target of making this kind of arrangement is that we need to have a unit that can concentrate the solar energy which is falling into it without having to do tracking for the sun, so that any amount of energy which is falling within this angle, 2 theta c, from here to here, is expected to be reflected on that absorber surface that we have here. You can see that between this angle and this angle, anything that's going to fall in, it should be reflected inside here, either from this side or that side, as long as it is within this acceptance angle. So that is the main idea behind this. And the point here is that it would save a lot of burden of having a tracking system that has to be adjusted so that it can move to track the sun path in the sky. But as long as we are in this range, then you could guarantee that we are going to have energy falling into the receiver. And this energy is a multiplication. The multiplication factor is not too high. The concentration factor is not too high. It may not exceed the value of 10. But even having a multiplication of the solar energy that is falling onto the receiver by itself without having to do tracking, this is some sort of an advantage that we get for such a surface. So, talking about the upper ends of the reflector here, when should be the length of the reflector? We're talking about here a parabolic shape. This parabolic shape is extended upward until the surface, the tip of the surface here, this part is parallel to the axis of the unit. And the same thing here. So this is how it can be limited. I mean, you are going to extend the parabola until to the point where you reach to like a vertical line, not necessarily vertical, but anyway, it would be parallel to the axis of the concentrator. This is where you're going to stop it, and that determines the end of extending the parabola. This parabola is going to have an axis, and this is the axis of the parabola. So when I say the parabola axis here, you would imagine that this parabola is going to be extended, and accordingly, this is the axis of it. Similarly, it is done only for one side, just because of the figure would not get complicated. But for the other parabola, you can expect that you're going to have some sort of an axis right here. So that what we see exactly in front of us here is a case of a symmetry. Two parabola are going to be facing each other, intersecting at an imaginary point here, which is below the unit, but you stop it or you cut it earlier to that, and then you put your surface, receiving surface. Now, we have looked at this last time, and we said that in some of the applications, they would look at here that the edge here, the amount of energy which is falling in at the edge of this parabola here is reaching to the edge of the receiver, and the same thing from the other side. So the point here, this quantity of the energy which is reaching the edge is less than whatever is reaching in the middle of the receiver. That's why they thought that maybe they can save the material and cut this part off, so that the height of the collector could end here at HT, and the T here stands for truncating. So you are truncating part of the material out so that you can save the material. Is it going to affect the performance? Yes, but not significant. Accordingly, it can be some sort of an economic solution of reducing the price of the collector without sacrificing the performance a lot. And we have seen this, we talked about that last time, we have seen that in expression of this figure, that if you are talking about a perfect surface, and this surface, as long as the angle is between 0 and theta c, then you expect to have this 100% of the energy falling into the aperture is reaching the receiver. After that, 0 is reaching. But if you are going to truncate it, then you can extend the amount of energy a little bit here as you are proceeding, which means that you can still have energy falling into the receiver at angles greater than theta c, because simply the value of the theta is going to change. I mean, if you theta here is between that axis and the line extending from the edge of the receiver through the focus until the upper edge of the opposite receiver. If we're going to end it here, then what you would expect, the value is going to change. You are going to talk about a value of phi t rather than theta c. And accordingly, you would expect more energy that is reaching here or that's falling here to reach on the surface. That's why it's extended a little bit behind this angle theta c. The effect of truncations, this is what we have seen there. And then the performance characteristics of this absorber have been plotted in 3 figures that would provide us with the height to aperture ratio, the height of the ratio to the aperture. To remind you, the aperture basically is this kind of opening at the top, which is 2A. This is our aperture here. And this is the 2A dash, this is the receiver. So, or this is the distance here, and that's the distance here. So the value of H divided by 2A is provided here in this figure. So height aperture ratio. And based on the concentration ratio, or as a matter of fact, based on the angle theta c, you can see what will be the concentration ratio. Or in other words, for the case of full CPC, as we'll see in an example here, if you are talking about a full CPC which is at an acceptance angle of 12, then at this acceptance angle, you can determine what should be the concentration ratio and what should be the ratio between the height to the aperture, so that in case you are designing a unit then and you are looking for a certain specific concentration ratio, you can reach it by knowing what would be the angle. Or the opposite, if you have the angle, you can determine what would be the concentration ratio. The next figure is ratio between the height it's basically the first one was the height to the aperture ratio. This one is going to be the reflector area to the aperture area. And the same thing, this is the acceptance angle. In the x-axis, we have the concentration ratio, and in y-axis, as I just mentioned, it's the ratio between the reflector area and the aperture area. The reflector area basically is supposed to be this side area that we have here. Definitely, I'm talking about the internal area of this part, which is taking the parabolic shape. The third figure, or a characteristic of this type of collectors, is the ratio between the number of reflections, the average number of reflections, versus the concentration ratio for, again, different acceptance angles. And there is a certain set of a minimum number of reflections, which is given here as 1 minus 1 over C, where C is basically the concentration ratio. So these are some sort of characteristic figures that you can join or you can relate the concentration ratio. You can to dimensions. The dimensions could be ratios of the areas, and ratios of dimensions, lengths like h over aperture length, or ratio of the areas, or the minimum number of concentrations, the minimum number of reflections, I'm sorry. And maybe I showed you a figure last time that is showing how this arrangement, or how the kind of reflections is being done. This is the figure to the right here. Some of them are going to have exactly one reflection, some does not need reflections at all, and taking the average of these is going to result in the average number of reflections, as you can see here in this figure. So those figures, however, might provide us with values that are less accurate. As you have seen previously in dealing with the figures, figures are easy to use. You can easily obtain values out of them, but there's an associated problem with the figures, which is the accuracy. If two of us have started to use the figure, you might get different results. So that's why, and in the case of you want to do some sort of programming, then you need these figures to be reflected in the form of equations. And the equations that we have in front of us here are basically a translation of the method that we use for estimating, for example, the concentration ratios or the area ratio. This is all given in terms of equations. Okay. So equations that are extended from 2 onward are these equations that are relating those results that we have seen in the figures in a mathematical form. The first 3 of them, equations 762, 763, and 764, are basically handling the full CPC, whereas the truncated ones are shown in the next equations that you see, starting with equation number 1, and that's even why you see the value of the subscript AT. The T here stands for truncated, which means that it is the collector where the height has been only the value, or considered to be the value of h sub t, only the truncated height, not the full height. The full height relations are given in the 3 first equations, whereas the truncated height relations are given in the following equations, as you can see here. Ni is the number of reflections that you can have in the system. And it is given here as a function of x, and x is given as a function of the angle and the ratio of the heights, the truncated heights, to the full height of this of the CPC unit that we have. Let's look at an example here. The example is considering a compound parabolic concentrator is designed with a concentration ratio of 2. So here we are knowing initially that you need to design a unit, and this unit should have a concentration ratio of 2. He's asking us here to prepare plots of theta c, phi, ART, and HR and N as functions of the ratio between the truncated height to the full height, like H over or HT over H. What we might be interested in here is just to look at the procedure. I mean, this kind of process is being done so that you can generate figures like the figures that we have seen, not exactly like the figure that we have seen earlier, but something like which is basically in that kind of dimension. And what we are going here is to utilize the defining relations and the equations that we have seen a while ago, so that we can get this kind of relations for how the parameters are going to change as we are changing the difference ratio of the height, HT over H. Now, if you do remember that the concentration ratio has been defined as 1 divided by the the sign of the angle or the acceptance angle. The concentration ratio is given here as 2, so that accordingly we can get the value of the angle theta c, which is sine minus 1 of 1 over 2. 2 here again is the concentration ratio. Accordingly, for a concentration ratio of 2, you expect the angle, acceptance angle, to be 30 degrees. Knowing this value, we're going to substitute into the expressions of the equations that we have here, which are basically this set of equations. This one is talking about the areas, aperture area and receiver area, knowing the value of theta as calculated as equal to 30. And where did we get the 30 from? We got it from the definition that we have seen earlier, that Ci, the concentration ratio, is 1 divided by sine theta c. We know that Ci should be 2. So 1 over sine theta c should be 2, which means that sine theta c should be half, 0.5. And if the sine is 0.5, then the angle is 30. So this is how we came up with the value of theta c initially. Then, knowing the value of Ci and the value of theta c, we can start substituting. Definitely, we can use this figure. For example, you can start with a value of equal to 2 as the concentration ratio, and the intersect is going to be here. So you can roughly or visually estimate what should be the angle. And when we say the angle is 30, yeah, because we calculated, now we can say, yeah, it makes sense. This point is 36, this point is 21. So this point is closer to this. Maybe you can use a ruler to measure this dimension and that dimension and do some sort of a ratio so that you can come up with a value which might not be exactly, but it will be close to a value of 30. And the ratio between h and the aperture area A can be obtained from here. Take a horizontal line from here until it intersects here, then it will be 2 point something. And then according to this dash here is 3. So we're talking about something close to 2.3 to 2.4 like this. But then we can use it here for a concentration ratio of 2. You can determine what should be the ratio between, or what will be the average number of reflections. You can use it here to get the ratio of the area of the aperture, area of the reflector to the aperture area, or you can use it here to obtain what is the height of the aperture, or h over a ratio, so that at the value of 2, you construct a vertical line to hit the dashed line that represents the full CPC, move to the left, and then you can get this h over a ratio. So this is how you can get it visually from the graph, whereas you can get it from the equations by the substitutions that we have done a while ago. We started by determination of the value of theta c, finding it equal to a value of 30. Then you can get the ratio between a and a dash. And you can get the value of f, substitute f in this equation to get the value of h. Then the value of phi t, which is usually twice the value of theta c, and then you can get the rest of the values that we have here. What if we are talking about a truncated collector? Then you can definitely obtain the other values. What will be the value of AT, and what would be AT basically is the aperture area of the truncated collector. The value of HT, what is the H of the truncated collector, and accordingly N, which is the number of reflections. So this is basically what you would do for solving a problem like this. And if he's looking for, so this is basically the kind of values that we have here, and we get the required numbers that we have, and then you get the value of HT over H among the values that we have obtained already. And in our case, when we did the substitution into the equations that we have, we got a ratio of HT over H equal to 0.5. Then he's looking for what would be the different values if this HT over H changes. So in our calculations, we got it 0.5. So we got this value of n, this value of theta c, this value of ht, this value of a r for the truncated one, and the value of phi. Then what if the value of ht over h has changed? Then you are going to be doing some sort of an iterative. Normally we do something like we do through a program like ES. We just take the ratio of ht over h as a parameter, and we do a parametric table, and accordingly we get the other variables as being calculated, and then we plot it all together. What we see here is something slightly different. It's the same idea of compound parabolic concentrator, but it does not end with a flat part at the bottom, but instead it ends with a cylindrical shape. And it is being done in a way that all the energy which is falling within the acceptance, within the value of the acceptance angle is going to fall into this cylinder here. Why is that good? Because it allows us to pass a fluid inside the cylinder, and the fluid is going to be heated. What we see here is a two-dimensional view of the collector, and what you would expect basically is something like you see in this figure. If I'm talking about a collector, say the collector is like this, this is a straight part, then actually it will be extended in this direction this way. And then the energy is going to be falling into it within the acceptance angle right here. And then you can have all the reflections that are falling in. Having it to be done in a cylindrical shape, which is this one, so that the reflections are all going to fall on this cylinder. And I just copied this from the some presentations and or some actually sites on the internet that were trying to show that the reflections are expected, all of them, to fall into that cylinder that you have here. And accordingly, you're going to have multiplications of this CPC units that are stacked together, and the tubes that are passing in the vertex of the CPC unit here, and then you have a fluid here which is going to be heated. So this is another arrangement. They have different versions of this, and this is one of them. And this is practical in the sense that if you have a fluid and the fluid needs to be flowing inside a tube and you need to heat it up, you can do it with this. You don't have to use a parabolic trough collector that needs tracking. You can use this one, but you would know that the concentration ratio that you are going to get is going to be limited somehow. You cannot get everything. So we just left tracking behind, and accordingly, we got concentration, but it will not be as high as what you'd expect with tracking. And inside that unit, inside that cylinder, it's not necessarily a single tube, but it can be a couple of tubes, as you can see here. The tubes can be, or this whole tube that we see here can be even evacuated. Why evacuated? We have seen that before, that when you evacuate the cylinder from inside, and you have a couple of cylinders that are having the fluid passing through, then having this part made or evacuated vacuum, it means that we are eliminating convection and conduction losses. And accordingly, you can get better performance, more energy falling into the unit and less energy loss from the fluid inside or the pipes inside or the receivers inside. Accordingly, you can have higher temperatures attained. And what you see here is this double glass indicates that there is evacuation here in between the two surfaces of the cylinder here, the concentric cylinder, and inside here you can have a pipe or a couple of pipes, as you have seen in the previous figure. So this method can, the way we do here, you can generate or you can make a CPC unit with any convex shape. They are not necessarily parabolas. It can take any shape, and it allows us for a range of variations. You can do it in a way, but the thing which is very important here is that while you are making this unit, you should make sure that it is designed in a way that the reflections of the energy falling into that outer shape should fall necessarily into this tube. And that's how actually you are making the multiplications or the concentration ratio increase. The flow inside the tubes here can be arranged in a way that you have fluid passing in series or in parallel. What are the differences? Basically, in parallel, you are distributing the flow here. If, say, for example, you have an m dot passing here of the fluid, the m dot is going to be roughly divided by 3, so that less amount of energy is going to pass here compared to this, compared to that, and they are going to be combined at the end. Whereas here, you are allowing the whole mass flow rate to be passing like in a zigzag form. And that's what we call a serial kind of arrangement. And this is like a parallel kind of arrangement. So again, it allows you to do both series connection and parallel connections of the tubes. That was actually, I obtained this from one of the figures where they show that they can have different arrangements. And the multiplications here, you have 3 types of CPCs that are placed side by side, and showing that there are different kind of arrangements for the flow that can be done whether series or parallel. The advantage of CPCs, I repeat it again, is that you do not need tracking. So you can have concentration of the solar energy which is falling into the unit. You can have effective heating without having to put a mechanism to track the sun. However, they should be properly oriented so that anyway the energy falling into it should be in between the acceptance angle. Otherwise, nothing is going to reach to the surface, or whatever is going to reach the receiver would be less. So the proper orientation to maximize the absorbed radiation is an important factor here. The operation at any time should be determined so that you would know what would be your best orientation of the collector that you have. Accordingly, the absorbed radiation, we should be able to calculate that. So a critical question would be, shall the beam radiation all be absorbed or only a part of it, or what? And accordingly, they came up with a logical orientation of these collectors, is that the collector would be oriented on an east-west axis, which is sloped toward the equator, so that it would be facing the sun. More or less, you can adjust it around this axis. The CPC would be arranged so that the incident of angle of the beam radiation is going to be within a certain limit of plus or minus theta c, the acceptance angle, so that you can make sure that you are making use of the maximum amount of energy that you can get from this unit. And the angle of incidence is going to be in the north-south vertical plane. You will be seeing that in the figures that we are going to show in the next slide, so that you can imagine how does it look like. But once we know that, once we do that, we should be able to calculate the amount of energy that is falling into the absorber, and the amount of energy which is basically absorbed here, which is capital S, as we used to write it before in the previous chapter, is going to have the 3 components as we did earlier. One component is the beam radiation component, the second is the diffuse radiation component, and the third is the ground reflected. Are we going to have ground reflected? Yeah, it depends on the angle. So at a certain angle, you may have beam radiation only, or you may have beam radiation and diffuse radiation, or you may have beam radiation, diffuse radiation, and ground reflected radiation. What's the condition? The condition is given here in the equations 771b, 771c, and 771d. So these 3 equations here are estimating the values of GB,
B here stands for beam radiation of the CPC, GD, diffuse radiation of the CPC, and G, which is ground radiation component of this collector. Values of these are depending on beta and theta C. Beta is the inclination angle of the collector, and theta C is the acceptance angle. So if the acceptance angle plus the angle of inclination are less than 90, then you would get a value of diffuse component. You don't have a value of ground component. If they are greater than 90, then you are going to have both components as given here by these equations. Once you know the values of GB, CPC, the beam component, the diffuse component D, the ground reflected component G, you can substitute them in the equation 771A to calculate the value of S. I have to mention that when you look at equation 771B, which is GB of the CPC, is equal to F, capital F, into G, beam component, normal, multiplied by cosine theta. What's the F here? We call it a control factor, because here it depends that the value of F, if it is within the range, then you expect beam radiation to be falling and absorbed and resulting in concentrated energy. If it is not within the angle, then a value of F would be equal to 0, as again, we'll be seeing in the next figures here. Then the values of tau CB, tau CPC, and alpha are properties of the surface that are going to be determined according to the next slide. The first term in equation 771A is the beam contribution to S, which is basically this component that we see here. So as I just mentioned it earlier, that this part here is representing the beam component. This part is the diffuse component, and this part representing the fraction, which is basically the ground reflected one. So the first term has talking about the beam radiation contribution to S. The other one, or the second term, is basically diffuse, and the third term is the ground reflected radiation. In the first term, the GB CPC is the beam radiation on the aperture, which is within the acceptance angle. So this is talking about the component, which is this component. And this component is going to be estimated by that expression that you can see here. Tau CB is the transmittance of the beam of radiation of any cover which may be placed over the concentrator array. You may have a cover for your array. Why do we put covers? We normally put covers to reduce the amount of heat losses to the surroundings. So if you have a cover, then tau CB is going to be the transmittance of this cover. And alpha B here is going to be the absorptance of the receiver for the beam radiation. These are surface characteristics. The factor tau CPC beam is the transmittance of the compound parabolic concentration that accounts for reflection losses, which is a function of the average number of reflections. Each reflection, you expect some losses to be associated with it, and this is going to be accounted for in that expression of tau CBC of the beam radiation. The factors in terms of diffuse and ground reflected radiation are going to be similar, or analogous to that. So for each one of them, you are going to have that component have TC of the beam radiation component, then you expect to have TC of the diffuse component and TC of the ground reflected component. Tau CPC beam, you have tau CPC diffuse or tau CPC G ground reflected. Alpha B, you have alpha D and alpha G. So they are analogous to each other, and all of them are expressed by the nomenclature that's given here in this slide. Now this angle is going to reflect
the conditions that are given in the previous slide. So these conditions here, which are specified by this part, so that you can imagine how does it look like, it is represented in the figure that we are going to see for a while. Remember, beta is the angle of inclination of the unit to the horizontal, and theta c is the acceptance angle. Now, coming to this, so a certain collector here, which is inclined as an angle of beta here, and this is the value of beta. This line is representing it. Now it's with the zenith angle, and then beta minus theta c is going to be this. Beta plus theta c is going to be this, and this is basically is the acceptance angle that we have here. So the collector is placed in a way that would be something like this. And the energy will be falling into it. And now it depends for the values of beta and theta c of how much of the energy is going to be falling in. So two angles are the angles that we are interested in, beta minus theta c and beta plus theta c. These are the angles from the vertical of the plane of the collector that providing the two limits of the acceptance angle. Again, the acceptance angle is this angle here, which is 2 theta c, this one. If the beam radiation is falling here or falling here, it will not get into the collector. And that's why the condition for applying the beam radiation is being given here. That's been given by Mitchell. So the value of tan minus 1 into theta z, this is the zenith angle, cosine gamma s, that's all should be within these two limits here, which are representing the two ends of the collector for the acceptance angle. So the value of F, or capital F, which is being used into the equation for the beam component of G, is actually dependent on this range that we can see here. If it is within the range, then the value of F is equal to 1. If it's outside the range, the value of F is equal to 0. What does this mean? It means that when you get to this equation, the factor F that we have here has to determine whether the energy, normal energy which is falling, are falling within the acceptance angle, so it will be concentrated, or it's outside the collector right away, so nothing's reaching to the collector and the F is equal to 0. So this is actually is limited to be within this range of the angle here, 2 theta c. Normal energy falling outside this, normal either from this side or from that side are not going to fall inside the collector, and accordingly there will be no collected beam radiation component. So if the beam radiation is incident on the aperture where the acceptance angle, within the acceptance angle, then F is going to equal to 1, otherwise F is going to equal to 0. You may have a transparent cover, as I just mentioned. The transparent cover not necessarily done on a single CPC value, but you can have like a series of CPCs that you can see, like what we have shown here a while ago, those ones, and then you can have some sort of a cover that can cover all of them together so that you can protect them all, or make a single cover that's going to be extended, which is the glass cover you can see here in figure A. So this is a cover which is extended over a certain number of collectors together, and that this way you can reduce the amount of heat losses to the surroundings, mainly by convection and radiation. This is the kind of suppression that you can expect. And if you have a cover, then the amount of radiation falling into the receiver is going to be reduced by the value of the transmissivity of the cover, which is expected. Then in this figure, it is representing the effective incident angle as a function of the acceptance half angle. So a part of the incident diffuse radiation enters the CPC, and that part depends on the acceptance angle. The relationship between the mean angle of incidence of effective diffuse radiation from the sky and the acceptable half angle is shown in this figure. And actually, the kind of, this is a range as you can see here, but the dotted line, which is like some sort of an averaging for it, has been represented by an equation, and the equation can be there so that we can use it whenever, instead of using the figure. So this is based on the assumption that diffuse radiation is isotropic. What isotropic mean? Again, to remind you, isotropic would mean that a parameter which is not, or a property which is not changing as the angle of the direction of the measurement is being done. The relationship between them depends on the nature of the cover system. The figure showed a band of solution, not a single one, but actually there's a range for each value of the acceptance angle so that you can get the effective incident angle. Including the case where you have one cover or two covers, refractive indices of, if you remember from what we covered previously, the refractive indices may have different values that are 1.34, 1.526, and so on, up to 0.0524. The equation of the equivalent angle of incidence, the dashed line equation here, is the equation theta E, as you can see it here. So what we have a relation between the effective angle here and the acceptance angle. So for a CPC with a value of theta C equal to 20, the mean angle of incidence is going to be, or the best mean angle of incidence is going to be 45, and the same thing applies for the ground radiation as well. CPCs are oriented so that normally the ground component would not be there unless it is tilted more to the ground so that it can see part of the energy falling from the ground. So actually it depends on how the orientation of your collector is going to be looking like. This is the collector, for example, and the ground is here. So how much of the energy coming from the ground is going to fall into the unit and be reflected back, that depends on this value. If you have more tilting upward here, you might not have any energy from the ground falling in. So now it depends on the value of beta that is going to allow for the ground reflected energy being used for concentration of the energy into the receiver surface here or not. So generally speaking, CPCs are oriented such a way that you do not utilize any ground radiation. But you know, as we mentioned, that it depends on the angle. If the CPC can see the ground, then you can have a component of effective amount of radiation or ground reflected radiation falling into the unit. The terms that we have seen, that tau CPC B, tau CPC diffuse, and tau CPC for the ground reflected radiation that we have seen in equation 771A are transmittance of the CPC that would account for the specular reflection of the concentrator and the average number of reflections inside, and an expression that can be used to determine the CPC is the reflectance, which is raised to the power Ni. Ni is the number of reflectance that we have. So reflectivity to the power of the number of reflections that we have in the unit. And we have seen the equation earlier that can provide us with the value of Ni. The average, Ni is the average number of reflections in the collector. The absorptances, alpha B, alpha beam, alpha diffuse, and alpha ground reflection of the receiver surface depend on the angle of incidence again. If the angle of incidence vary, depending on the angle of incidence of radiation to the aperture of the CPC, the number of reflections undergone by the radiation, and the shape of the reflecting and receiving surfaces. So it depends on geometry as well as the angle of inclination. If you have a small number of reflections,
It will be for large acceptance angles. And then as a first approximation, the absorbance can be taken as corresponding to the angle of incidence of the effective radiation on the aperture. And that basically is going to affect the value of alpha. Now, let's have some sort of an example that's going to clarify that more. And the example here is 771. What we are looking for basically is considering an uncovered full CPC collector. So it's not truncated, it is not covered. It is mounted on a horizontal east-west axis, oriented as a slope beta is equal to 25 degrees from the horizontal. The latitude of the city where the collector is placed is 35 degrees north. The acceptance angle 2 theta C is 24. And we are making the measurements at 10 o'clock in the morning on the 1st of August. The beam normal radiation has been measured to be 805 watt per meter square. What is needed is to estimate how much is the beam radiation incident on the compound parabolic concentrator per square meter of the aperture area. So in this example, we see a link between the information or the characteristics of the CPC unit and the location and the hour of the day where the energy is falling. So the first step, now what he's looking for the beam component only, which means that if you go back to the slides, which are describing the relations here, what the example is looking for is only the expression given by equation 771b. He's looking into this component alone. To get this component, then we need to know the value of f. Is it 0 or 1? 0 or 1, it depends on the criteria that we have seen earlier. The value of GBN is already given to us, and we need to get the value of cosine theta. So these are the components that we need in order to estimate the value of GB. F can equal to 0 or equal to 1 based on a criteria which is given here. So in order to know that, we have to determine what will be the value of theta z and the value of gamma s. So we're going to go back again to the information that we have studied in chapter 1 for the determination of these angles, so that we would see the beta minus theta c that we have. Is it less than this value? The beta plus theta c, is it higher than this value? Or in other words, is this value here is somewhere limited by these two angles, then the value of SF is going to equal to 1. And the energy is going to fall into the aperture area. If it is, if this condition is not met, then there's no energy or no beam radiation component will fall into this collector. So what we are going to do here is basically calculate the values that we would like. The zenith angle is dependent on the value of the inclination angle and the solar angle. Back again to the information, as I mentioned, that we have studied in chapter 1. The declination angle is 23.45 sine into 630 multiplied by 284 plus n divided by 365. What is n? It's the number of the day on the year, starting from 1 at 1st of January and ending with 365 at 31st of December, except for a leap year, then it becomes 366. So we're talking about 1st of January, so the value of n, the day number is 214. And that's from table A16, if you remember, in table 16, chapter 1. So for 1st of Augustus, n is equal to 213. Omega, the hour angle, is 15 into the solar time that we have, minus 12. We're talking about 10 a.m. solar time. So 10 minus 12 is minus 2 into 15 is minus 30. The declination angle, if you substitute the value of 213 as n here, you can get a declination angle of 17.9. From this, you're going to substitute into this equation 165 so that you can calculate the value of the zenith angle. And the zenith angle has been calculated as 31.6. Then, the value of gamma S, the solar azimuth angle, is given by that expression, and this is again obtained from equation 166 in the book. So gamma X is basically equal to a value of minus 65.2. Then we can look at the parameters that we are going to measure this against. We are going to measure against beta minus theta c and beta plus theta c. Beta is 25, theta c, the acceptance angle is, or half acceptance angle is 12. So 25 minus 12 is 13. Beta plus theta c is 25 plus 12 is 37. So the value that we are going to calculate, which is tan minus 1 theta z cosine gamma s, should be in between the values of 13 and 37 for the beam radiation to be calculated. Otherwise, the f is going to equal to 0. How we can verify that? We calculate tan minus 1 of the zenith angle, cosine of the solar azimuth angle, and the value calculated was 14.5. The 14.5 do exist in between. It is greater than 13 and it is less than 37. So the value of f, the control factor, basically is going to be equal to 1. So beam radiation is going to be accounted for. Then we need to calculate the value of cosine theta, which is the incident angle. We are going to go back again to chapter 1 and get the value of cosine theta. Cosine of the incident angle is cosine phi minus beta. Phi is the latitude of the place, which was specified as 35 here. Beta, again, is the inclination to the horizontal. Delta is the declination angle, and omega is the solar hour angle. Accordingly, you would calculate the value of cosine theta and get the value as 0.865. Now we are in a position that we can substitute into the expression of equation 771b, so that GB, the beam component of the radiation falling into the collector, is going to be equal to F. F is equal to 1 because we have satisfied the criteria already. And GBN is given to us, which is 805, and the cosine of the inclination of the incident angle has been calculated as 0.865. Accordingly, the value of beam radiation which is falling into the collector is 700 watt per meter square. So definitely you can repeat the example for any day, for any hour of the day, and for any latitude angle phi, and definitely for any value of beta or inclination to the horizontal. Now let's extend this example a little bit, in which we would be interested in the calculation of more than the beam component. So at the location and time of the example that we have covered earlier, so now again, the same latitude angle of 35, the same day of the year, which is August 1, the same hour, which is 10 o'clock in the morning, we would need to determine. Now the diffuse radiation on a horizontal surface is given by 320. So this is basically G sub D. The CPC of the example is truncated and it has a concentration ratio of 4.5. The reflectance of the CPC reflector is 0.89 and the absorptance of the receiver is 0.94. Estimate the total radiation absorbed by the receiver per unit receiver area if the CPC array has a glass cover with KL equal to 0.0125. If you can see here, and that's something probably is been mentioned earlier, that what we are considering here is essentially, it's like, you know, the Lego game. It's like a building block. Whatever we have used in terms of the angle definitions that were, and the calculations related to it that we have covered in chapter 1 is going to remain with us all the time. And the same thing applies for the information that we are collecting over the chapters. So each time we are building on it so that in our calculations and our estimations, we might need the information that we have gathered in the previous chapters. So for the circumstances that we have, the value of beta plus theta c is equal to 37. If you remember, beta was 25 and theta c was 12. So beta plus theta t is given here. So there's no contribution of the ground reflected radiation. And that's something which is given in the conditions. So accordingly, what the contribution that we have here is limited to beam radiation contribution and diffuse radiation contribution. Then the value of the GD is calculated or is used in equation 771C to estimate the effective diffuse radiation. So the diffuse radiation that's given here as 320, and the concentration ratio is 4.5. We have calculated the beam radiation angle actually, so that cosine is 0.865, which is the one that we have calculated here. Cosine theta is essentially 0.865. If you are going to use your calculator, then the value of theta then is going to be 30 degrees. So the angle of the beam radiation which is falling is 30 degrees. The transmittance of the cover of the radiation from figure 531 is going to be 0.9. Then we substitute into this expression here. And remember, in that expression here, what we have basically is the combination of only this beam component of the radiation and the diffuse component of the radiation. The mean angle of incidence is 45, if you remember the figure that we have covered a while ago, which is also can be interpreted in terms of the equation, the one which is given as a range here, or substituting into this equation here. If you know the value of theta c, we can get the value of theta e. And the average number of reflections is 0.81. Now substitute into the expression, and then you can get the value of S here, which is the amount of energy that is falling or absorbed by the CPC unit. And this has both components of beam and diffuse component. Is that okay? Are you following me? I'm not getting any comments or questions so far. So وهتكونوا نمتوا يا شباب.
يس دكتور.
معاك
يس نمتوا ولا لسه معايا؟
معاك يا دكتور.
طيب okay, fine. I would probably mention that what we are doing here, or probably that the chapter that we are in is going to be representing the coverage that we are going to have for the course. Maybe next time, if we have time, I can talk briefly about the issue of energy storage, but that would be it, since our last day of class is going to be next Monday. Our class on Wednesday is going to be relatively short. Why is that? Because we have a quiz, as we mentioned earlier, and that's something probably I would just mention that for the sake of the quiz, we just had 2 quizzes earlier. The third one is going to be on Wednesday, and we may have, or actually I'm planning to have another quiz that's going to be next Monday, but it will be optional. If you did well in the 3 quizzes that we had earlier, then that would be it. If you need to improve one of them, then you can join the next one. And let's have the next one also related to chapter 6, which is the flat plate collector. So both the quizzes, that the mandatory one on Wednesday and the optional one coming on next Monday, are going to be related to the same chapter, chapter 6. The time is short to provide
another homework probably. So probably related to chapter 7, I need you to focus on the examples that we are covering here, because we are going to finish our classes on Monday and the exam is going to be on Thursday. So it's not a long period before we finish the exams and finish the classes and start the exam. So I think that will be it for the homework. The next one, or the one that you have in hand, which will be submitted on Wednesday, would be the last homework. I may give another homework, but I don't expect you to submit the solution. So I'm going to give like homework on chapter 7, which will be made of 2 problems, but no submission. It is just for your practice, so that you would just, I'll provide the quiz, the homework maybe on Wednesday, and post the solutions on Saturday, so that you can just have additional practice added to the 3 examples that we are covering here in this part of the chapter, or the number of examples that we covered in the chapter as all, so that it can provide you with an opportunity for additional practice problems. This is on one hand. On the other hand, when it comes to the project, I think the example that we have had previously related to the calculations or utilization of the F-chart method is simple, and you can just follow the example I've given, and the only difference is going to be related to the place that you are in, or the city that you are assigned to work with. So it's some sort of a standard procedure that you have to go through. You may do it at least the first couple of calculations you will need to do by hand, but you can do the rest in Excel file, and the calculations can be done similar to what we have done in the example. The program of the red screen that I was referring to, it's a fairly simple program. When you download it from the internet, then you are going to have 2 options. One option is to subscribe and buy the software. You don't have to do that, but having not to do that, it means that you are going to get like a trial version, and that trial version would not allow you probably to save your work. So you are going to do it, and whatever values that you are going to obtain from the collectors, you are going to, from the software, you are going to record it by your hand, so that you would you would just record the values this way, or you can make a screenshot if you want, like what I did, showing you the information of the solar information for the different cities. What I did is that I selected the city, and I can select it from the map or select it by searching, writing the city name, and after that go into the data section of the city, and then I would be able to get the climatic data, where I made a screenshot and I put it there in the file. The good thing about the program of the red screen is that it may do a parametric analysis for you. Meaning what? Meaning that on the screens, it will give you a recommended number of collectors to be used for the city that you have. Do you have to stick to that? The answer is no. You may do it differently, in the sense that suppose that you have taken a case and it has recommended 14 collectors to be used. Say that we are talking about flat plate collectors. And for the collectors, you have a very large database where you can select between maybe tens or hundreds of collectors. I'm not putting a restriction in that, it's all up to you. But whatever you make a selection, you have to put it clear that this is my selection for my problem. Then there is a window, or there is actually a place where it gives you the recommended number of collectors, but you don't have to stick to that, as I mentioned. And accordingly, you may do some sort of a parametric analysis then. Suppose that it told you that you need 14 collectors, and the 14 collectors have given you a solar fraction of 60%. If I were you, I would say, well, what if I use 20? And then I record the solar fraction. What if I use 25? I record the solar fraction. I may keep on increasing it until I get a solar fraction of 100%, for example. And then I would know if I need to cover all the load that I need for water heating.
using solar collectors without the reliance on electricity or diesel boiler operated boilers or natural gas operated boilers, whatever, then this is the number of collectors that I'm going to have. And the software does the calculation for the payback period, as well as the savings in the greenhouse effect, the CO2 gases. There is in the Blackboard a video that has been published by the RedScreen developers that will guide you through a step-by-step what you need to go from step number 1, step number 2, step number 3. You'll find that it's a very easy to follow kind of procedure where you can do the calculations. So the calculations that are going to be done by every team of you is going to have 2 components. One component is talking about the hand calculations that you are going to do by your hand, or maybe you can do it by your hand for the first month, and then for the rest of the months you can just put it all in Excel, and then the calculations can be done automatically through the Excel. And after that, I would not recommend you that you do the changes of the number of collectors. You can still do it in Excel as I did it in the example that we have, so that you can change the number of collectors and everything will change to tell you what will be the solar fraction. But this is done nicely and easily in the software as well. The expectations is that it's a special assignment or a project. So I would expect you to provide me with some sort of a report, which is short one. You don't have to put many details. It is not really a detailed kind of term project where I would ask for an introduction and calculation, but just simple introduction to indicate what are you doing and which city that you are considering, and then a brief description of what are the formula that you have used for your calculations. And after that, the results would be, you can give it in a table, and the table is going to calculate the value of the solar fraction, and then screenshots that can show the calculations that are being done for different, or for utilizing different number of collectors and the corresponding value of the solar fraction. You may take it one more step by making a plot that you are going to collect from these screenshots. For example, for a certain number n collectors, say 15, you are getting a solar fraction of 60%. If you made them 25, you get a solar fraction of 72%. If you made them 40, you get a solar fraction of 85%. If you made them 50, you can get a solar fraction of like 98 or 99%. And then you can make a plot that will give us an idea of, based on the solar fraction that you want, how many collectors you would use. The software, as I said, it is going also to provide you with additional information of the payback period and information related to the CO2 gases savings, how much are going to be. Let's say that the deadline for providing this special assignment would be the last day of classes, which will be next Monday. And I'm going to specify an office hour on Wednesday from 12:30 to 1:30, and on Thursday, but on Thursday it's going to be right after Dhuhr prayer, because there is a defense after that starts at 1:30. Oh yes, we can still do it at the same time so that you don't get confused. So 12:30 to 1:30 is going to be my office hours on Wednesday and Thursday, in case you have problems related to the to this problem or this special project. So that's something that I just urge you to start on it early, so that you can finish it early if you have not yet started already. Any inquiries or questions? Yes.
May you explain the project, like what is given, what is required more? Because it's kind of not clear.
The point here, what I want you to do is to follow exactly what we have done in the examples that we have for the F-chart method. what we are looking for basically is we have a hotel in hand. This hotel has certain number of rooms, and the daily consumption of hot water is being given for your case. I mean, which is the same for all of you. Suppose that we need to heat a certain number of liters per day up to a certain temperature, which say it's 65 degrees or 55 degrees, whatever. I don't remember exactly what is the value. So the point is, we need to make a selection of a set of solar collectors that are going to be heating this water to this temperature. And when I'm saying that we need to get the solar fraction, I would simply say that how much of the energy which is going to be needed can be covered by solar collectors. Do we need 100% of it? Or we need 60% of the energy given by the solar energy, and the rest is going to be either by electric heater or by use of a boiler? So this is what I mean by the solar fraction. So basically, you are a consultant to a hotel owner who approached you, and he said that I'm using electricity for my for heating hot water in my hotel, and the electricity bill which is coming to me every month is too large. Can we save on this by using solar energy? So what you need to do is say, I'm going to study it and come back to you. By studying, you are going to do exactly what is being done in the example you followed by the F chart, which is you're going to take a certain month, look at how much is the load of heating for this month, how much is the energy falling in this month. Based on the collector's characteristics that you are going to use, you are going to calculate the values of capital X and capital Y and substitute into the F formula. So you can say that by using these collectors, I'm going to satisfy a certain percentage of the heating needs by solar collectors. This is the solar fraction that I mean. Maybe what we can do, we can start our next class, the first 10 or 15 minutes. I'll be talking about this project, but I urge you to try to start on it so that if you have questions, you can raise it by the time I would just go through this process again and what you expect it to do as 1, 2, 3, 4.
Doctor,
Yes.
there are some details that I'm not sure how to use them, like the number of rooms and the occupation rate. There is the minimum outlet water temperature and the maximum temperature.
For
Does
you,
the difference require?
Yeah, the number of occupants and the occupation rate and this thing, you don't have really to do something with it if you have how much is the amount of water as liters per day. These are basically used to calculate how much water is needed. So just looking at the average need of a person in our calculations, any person would require per day, for example, 110 liters of hot water, and the hotel has 100 rooms. Each room would have an occupancy of 2 persons, which means that each room would require 220 liters per day. And is all the rooms filled every day? No, it's an occupation rate of 70%. So this is all a way that you can estimate how much water you need per day. But I've given this value specifically there. So the number of rooms and occupation rate, that's something you don't have to worry about, because it is all needed for calculations of how much water will be needed per day, and this is given explicitly. So it is just given for the whole picture to be clear for you, so that you can imagine or relate that to something which is actually located. And this, by the way, these are information for one of the actual hotels in the kingdom. So I just wanted to put it as full as possible, but for you in your calculations, this is all not needed as long as you have the quantity of how much hot water is needed per day. I hope it's clear now, Hussein.
Yes, Doctor, it is now clear.
Fine, okay. So get started on that. I'll be talking about that in our next class at the beginning, just for giving another hint or a boost for it. And as I mentioned, Wednesday and Thursday, the office hours will be dedicated for this. So that would be it for today. And we'll see you next time, inshallah, shabab.
No office hours today, Doctor.
Today, actually, it will not be a complete office hour. I might be available between 12:30 and 1 o'clock because of a meeting. So it's just half an hour. If somebody needs to reach me more than this time, just email me and we can specify a date that we can talk about. So whatever you want.
Okay, thank you very much.
You're welcome.
Doctor,
Tfaddal.
when will be the submission of the project?
It will be next Monday, last day of classes.
Next month.
And every team should provide only one. So it's not every team should provide only one report. In that small report or short report, I need you to mention what is the contribution of everyone. Like one did this, one did that. So that's something I just need to get an idea of.
Thank you so much.
Okay, welcome.
Thank you, Doctor.
Thank you, Shabab.